Okay, we're getting into our last section here, 2.7, graphing linear inequalities and absolute value equations and inequalities. And then last section, new section we're covering, we're going to have a couple days of review, and then we take the test on Friday. Starting out with here, inequalities and absolute value inequalities. Basically, those are the boundaries. And then all the points either above or below them are going to be the solutions to those absolute value inequalities and linear inequalities. One thing you got to remember is this: if it's less than or equal to or greater than or equal to, that boundary is dashed or a dotted line. If it's less than or equal to or greater than or equal to, the line or the boundary itself is also part of the graph, so it's a solid boundary. And let's jump right into graphing one here. Identify intercepts and slope. Okay, well, this one's in standard form. AX plus BY, we'll say equals C. It's the same thing as greater than C, whatever. So let's find our X and Y intercepts. So first of all, plugging in 0 for Y. 2X plus 3 times 0 is greater than 6. Basically 2X, we'll just say is equal to 6 because we're looking for X and Y intercepts. My x-intercept is 3. So I'm going to put a point at x equals 3 right there. Do the same thing for the y-intercept. You're going to plug in 0 for x, so 2 times 0 plus 3y, we'll say just equals 6. That means 3y equals 6. Divide both sides by 3 and y equals 2. So there's our y-intercept, our x-intercept. Put my y-intercept right here. Going back to the original equation, 2x plus 3y is greater than 6. This is a dotted line. Looks something like that. Now, we're either going to shade above the graph of the boundary or below it. We need a test point. Most of the time, we just use 0, 0 here. The only time you can't use 0, 0 as a checkpoint is if your line goes right through the origin. So test 0, 0. Plugging those in for the y and the x. 2 times 0 plus 3 times 0 is greater than 6. Well, is 0 greater than 6? This is false. So I'm not going to shade below the line. This point is not a solution. All our solutions are above the line. One other thing here. How do you find slope? Let's just say equals 6 for right now instead of greater than. Solve for y. Subtract 2x from both sides. 3y equals negative 2x plus 6. I can't add these two together. They're not like terms. And then finally divide everything by 3. I get y equals negative 2/3 x plus 2. Here's my y-intercept again, but there's my slope, negative 2/3. Need to be able to find slope. And you could graph it this way also if you wanted to in slope-intercept form. X and y-intercepts again. I'll plug in 0 for y first of all, negative x plus 2 times 0. We'll just say equals 4 for right now. Negative x equals 4, so x equals negative 4, dividing both sides by negative 1. So there's my x-intercept. Y-intercept. I'll plug in over here, 0 for x. I'm just going to say equals 4 because I'm just looking for the x and y-intercepts here. I end up with 2y equals 4. Divide both sides by 2 and y equals positive 2. There's my y-intercept. You could solve again for y right here if you wanted to. Add x to both sides and divide by 2 and put it in slope-intercept form to graph it. Either way is fine. But going with the original equation, it's greater than, so it's going to be a dotted line. my boundary. And then we need a test point again. Well, I'm going to use 0, 0 again as my test point. Plugging them into the original equation. Negative 0 plus 2 times 0 is greater than 4. So 0 is greater than 4. This is false. So again, I shade above. Okay, setting up a little word problem here. Manny has $15 to spend at the fair. It costs $5 for admission. 75 cents for each ride ticket and 25 cents for each game ticket, right? Inequality for the number of ride and game tickets we can go with. R equals ride ticket, G equals game ticket. Each ride ticket is 75 cents, so it's 3/4 of a dollar. So I'll say 3/4 R plus 1/4 for the 25 cents for the game ticket. It costs $5 for admission, so I'm going to put plus $5 here. And all of this has to be less than or equal to, he only has $15. So, cleaning this up a little bit, I'm going to subtract 5 from both sides. And then I'm going to get rid of the fractions. Get rid of the fractions. If you multiply everything by 4, it'll cancel out these two 4's down here. So multiply both sides by 4. 4 times 3/4 is 3R. 4 times 1/4 is going to be 1G. It's less than or equal to, and then 4 times 10 is 40. So here's what I'm working with right here. 3R, or 3 ride tickets plus 1 game ticket should be less than or equal to $40 basically, or 40 tickets, I'm sorry. What is the maximum number of ride tickets he can buy? Well, that is where I'd plug in 0 for G, so I'll say 3R plus 0 is less than or equal to 40. Basically, 3R is less than or equal to 40. Divide both sides by 3. And you get 13 1/3. So basically, 13 tickets. If you just get ride tickets, you can get 13 of them. What is the maximum number of game tickets? Well, I'm going to plug 0 in for 3, or R then. No ride tickets plus the game tickets is less than or equal to 40. This cancels out to 0, and G is less than or equal to 40. So you can have 40, a maximum of 40 game tickets. Okay, graphing absolute value functions now. Over here it's absolute value equation. I'm going to change it to this. F of x, we'll just say is greater than the absolute value of x. It's going to be a dotted boundary, and it's absolute value, so it's going to be a v. So just kind of plugging in some numbers here and figuring it out. You can see we got our table over here, so we'll plug in -3 all the way to +3, and you can see how the graph's going to look. F of x is the same as y, and for right now I'm just going to say equals the absolute value of -3. Plugging in -3 right here for x. Well, the absolute value of -3 is +3, so this y would equal +3. If you plugged in the absolute value of -2, you're going to get positive 2. Absolute value of negative 1, so on and so forth. You're going to get 1, 0, 0. When you plug in the absolute value of positive 1, it doesn't become negative. It's still, when you take the absolute value of a number, you get the positive value of it. It's distance from 0 on the number line. So 1, 2, and 3. Graphing these points, negative 3, 3, negative 2, 2, negative 1, 1, 0, 0, 1, 1, 2, 2, 3, 3. And here we go. It's a greater than symbol. You can see the vertex right here at the origin, 0, 0. It's going to be a dotted graph. And it's a V, and it looks just like that. Now, basically, we're going to shade this whole area below the graph or everything inside here. And the way we're going to decide that is, well, we need to pick a checkpoint. I can't use 0, 0, so I'm just going to use, I don't know, 4, 1 right here as my test point. I'm going to plug it in up here and see if it's true or false. Okay, so looking at this function, y is greater than the absolute value of x. Plugging in 1 for the y is greater than the absolute value of 4. Is 1 greater than 4? No, it's not. That's false. So I'm not going to shade below the graph here. I'm going to shade everything inside this V shape for my absolute value function. And all graphs kind of go off this same basic graph right here. Y equals, or y is greater than, or y is less than the absolute value of x. And then you just kind of shift your vertex over depending on what it's doing to the absolute value. And let's try one of those. Right here. I'm going to change this one up a little bit. I'm going to say this is y is, I'll say less than the absolute value of x plus 1. Okay, now most graphs, absolute value, start at the vertex. Well, the numbers that you're adding or subtracting to x on the inside of the absolute value shift the graph to the left and to the right. Now this particular one, it's plus 1. You always take the opposite of what's inside there. That's going to shift it to the left. So our vertex, I guess you could say, shifting the x value, that would be a negative 1. There's nothing outside here, so that's just going to be 0. So our actual vertex for this graph is going to be negative 1, 0 right there. And then it opens up just like the normal V. You can set up a little table if you want. I'll put negative 1 in the middle, 0 here. I'll also plug in 0, and I'll also plug in negative 2 for x, just to kind of see what the graph looks like to make sure it's opening up correctly. So if we plug in 0 in here for x, I'm going to get y equals, forget the inequality for just a minute, the absolute value of 0 plus 1. So y equals the absolute value of 1. The absolute value of 1 is 1. So 0, 1 is a point right here. Plugging in negative 2, the same thing. Plugging it in for that x, y equals the absolute value of negative 2 plus 1. Well, that's going to equal the absolute value of negative 1. That's still going to equal 1. Right here. You can see there's my V. Here's my vertex right here. It's a dotted line because it's just less than. And there's my graph. Now we just have to decide whether we shade inside, above it, or down below it. Well, I'm going to use 0, 0 as my checkpoint. Plug it into the original inequality here. 0 for y is less than 0 plus 1. The absolute value of that, that's basically the absolute value of 1 is 0 less than 1. That is true. So this point is a solution. So I'm going to shade everything outside or below it. We'll do a few more of these tomorrow. Have a good evening. See you tomorrow.